Anyway, so tonight it's a continuation from a week or two ago on complex numbers, and you know, this is new material for me to teach. So I don't know how it'll go, but the idea here is, in this series of talks, is to take basically someone who has gone through high school and may not have gotten the math that is necessary for quantum computing. So I'm going step by step, very slowly, and hoping that if individuals understand each of these steps, when they start reading the books on quantum computing, you know, where you're not spending days, if not hours, trying to figure out what people are talking about. And it really, I think it boils down to understanding some of the basics, like complex numbers, matrices, etc. So let me just review what we went over last time. I'll go over it fairly quickly. And then and I didn't really put it in the show notes, but it's really, trigonometry is quite important. And so I want to cover some of that. And then we'll get into polar coordinates. I'll spend a minute or two on Python, just to, you know, it's important to learn this stuff in the context of Python, because essentially, you know, we're in a Python world right now. And then we'll talk about a very special number, and you physics people probably know what that is if we get that far. So let me get right to it. Again, just as a, bear with me. Oh, shit. All right, well, I'll use the cursor. This is a bummer. Give me a second here. Why did that die all of a sudden? I don't have a backup plan for this device here. Let's just see if this happens to work. Oh, great, okay. Forgive me. Excellent. One more minute. So, that was. The story first, talking about complex numbers, and complex numbers are essentially an extension to the numbering system that we're accustomed to. And you know, it all starts when we're in grade school. We learn about this numbering line. Well, we ran into some problems in solving some equations, and we were running into equations such as x squared plus 1 equals 0. In other words, x squared equals minus 1. So, you know, to make the math work out smoothly, we needed to define a, you could think of it as a variable, but it's a constant called, we refer to it as I, which is known as the square root of -1. And sometimes in the engineering world, it's known as J. No different, it's the same thing, the square root of -1. And as we talked about before, we've got this form here where a complex number has a real part, A, and an imaginary part, which is B, where it's the complex number Z, for example, is A plus B times I. So A plus B times the square root of -1. So this is known as the real part, and in some programming languages and in some textbooks, you'll see it as RE, and that is the A. And in a second here, in some circles, the imaginary part B is referred to as IMZ, which is essentially B. Now, A and B can be real numbers. And what's really important in the quantum computing space is recognizing that I raised to the powers actually runs through a cycle of 4 values. So I to the 0 is 1. I to the 1 is I squared is -1, because square root of 1 times square root of -1 is, I'm sorry, the square root of -1 times the square root of -1 is -1. I cubed is -I to the 4th is 1, and I to the 5th is I, and you'll start to see the pattern repeat. And that goes on essentially forever. And this is an important thing to keep in mind as we go forward. And so how do we graphically look at or represent Z? We certainly can't use the standard number line. It is essentially really just one dimension. We'll use what's called the complex plane, and it's a grid with the standard number line going horizontally, and then vertically we've got the I values, or the imaginary parts. And before I go on, I do want to remind you that we had another way of writing a complex number from this standard form into an ordered pair form. So many books will, and this confuses people, will, instead of writing A plus BI, whatever the value of A and B are, they'll put in A comma B in an ordered pair form. So then what we'll do, I'm going to try this pen one more time. Golly. You know, it's kind of like when you debug programs, you just don't make any changes and you try it again a minute later, you just hope it works. Gee whiz. Yeah. Okay, so if I had the number 2 plus 2i, graphically it would be a point right here. If I had a number 2 plus 3i, graphically it would be at 2 and then 3i, so it would be here. Now, so let's talk about complex conjugates, or the conjugate of a complex number. Again, this is review, so I'm going to run through it fast. But if anybody has any questions, feel free. Just shout them out. But here's where it gets a little unusual. Here you've got a complex conjugate. The conjugate is essentially the complex number, but you reverse the sign of the imaginary part. So one thing to get in our minds is you've got the standard form of writing it is, you would refer to it as Z star or Z bar. And so if you wanted the conjugate of A plus BI, You could place that in parentheses with a star here, or you would, in some books, they'll put a bar over the top there. But the complex conjugate is essentially the complex number, but the sign of the real part, of the imaginary part, is reversed. And so if I had A plus BI, the complex conjugate would be A minus BI. If I had A minus BI, the complex or the conjugate would be A plus BI. Only thing that changes is the sign here. Now, in a perfect world, if I had my drawing mechanism here, what I would do here is, let's say we had the complex number 3 plus 2i, so that would be here. And essentially the conjugate of 3 plus 2i is 3 minus 2i, so that would be a point here. So you have the original point here, the conjugate point is here. If I had minus 1, 1i, the value would be here. Minus 1 plus I, the value would be here. The complex conjugate of it would be what? It would be minus 1 minus I. So it would be, the conjugate would be here. So essentially the points flip across the x-axis. So if I had a complex number of minus 2 minus I, the conjugate of that would be minus 2 plus I, and that would be right here. So it would flip over the x-axis, or the real axis is the proper way to say it. All right, so that's a conjugate. Now, the absolute value of a complex number, sometimes referred to as the modulus, is essentially just like the absolute value that we're accustomed to in our regular number line here. So if I had, if I was on this point in a regular real number, and I said the absolute value of 3 is the distance from 0, which is the origin here, is 3. Just like here, if I had minus 3, the absolute value of minus 3 is 3 points unit 3 away from the origin. Now, what about a complex number? Well, the complex number is essentially the same thing in that it's the absolute value, or the distance from the origin, but in the complex plane. So instead of the origin being, well, the origin for a real number line is here, and the origin for a complex plane is also right there at 0.00. So the question is, how far is that point distance-wise to 0? So if it was over here, minus 5 plus 2i, I'm over here. What is this distance right here? And so if I had a complex number a plus bi, the absolute value, or again, the modulus, is essentially the square root of the number times its conjugate. So to calculate it, it's the square root of the number, right here, z, times the conjugate, z star, or zi. And so if you kind of spell it out a little bit, I think you'll get like, you could get an aha moment here, is here, if I said, what's the absolute value or the modulus of a plus bi, it would be a plus bi times the conjugate of a plus bi, which is a minus bi, and we take the square root of that. And if you look at that, it should remind you of the Pythagorean theorem, which takes you back to the days where c squared equals a squared plus b squared, or c equals the square root of a squared plus b squared. I'm waving my hands right now, but instead of using the pen. So an important point to recall, since it's distance, the modulus, or the absolute value, is always a positive number. And here's where I would draw a line and show it to you. show the triangle, we'd figure out the length of the hypotenuse. And so, okay, those are two specific functions applicable to complex numbers. The conjugate in particular is one that is very specific to complex numbers. But okay, so how do we do addition and subtraction with a complex number? And that's very straightforward. If I have two complex numbers here and I want to add them, I simply add the respective real parts, and to get the real part of the solution, the answer, and then I simply combine or add the imaginary parts together as we normally add real numbers. So 2 plus 6 in this case is 8. So it's quite straightforward, quite frankly, when it comes to addition and subtraction. And here, for example, you have minus 3, minus 6, which would be minus 9. Here I have minus 1, essentially, plus 7, remember that, and I have plus 6. So the answer of combining or subtracting this complex number from this complex number results in this complex number. So it's essentially child's play. Now, multiplication, and I separate multiplication and division out because they are mechanically different. Multiplication of two complex numbers is essentially handled the same way that we've always multiplied, what are they called? I want to say compound numbers or something. You know, when we have A plus B times C plus D. We use what's called the FOIL method. At least this is what we typically learn in the United States, which is you multiply the first terms, you multiply the outer terms, then the inner terms, then the last terms to get your answer. So looking at the complex number 4 minus 5i times 12 plus 11i, you simply do the FOIL method as we've always done since, I guess, grade school. So that would be 4 times 12, and I'm going to do this in my head, which is 48, plus 44i, 4 times 11i, minus 60i, and then I do the last, which is minus 5i times 11i, which is minus 50i, minus 55i squared. I squared because minus 1, so that becomes plus 55. And whatever those numbers were that I said before, when you combine them, the 48 plus the 55, you get the 103, and you combine the minus 44 minus 60, you get the minus 16i here. It's a lot easier to do with a pen in your hand. So next we have the division, which is it's a little bit different mechanically, but the way you, man, I really need the pen now. The way you do this is, you know, really the strategy is you want to get rid of the complex number. You want to get the complex number out of the denominator. Recall, this is the numerator, this is the denominator. And how do you get the complex number out of the denominator? Well, you essentially multiply the number times its conjugate. And so if I had 2 plus 10i and I wanted to, and so what I'm doing is I'm taking this division right here, I'm multiplying it times 1. 1 being the conjugate of the denominator over the conjugate of the denominator, which in this case, the denominator is 2 plus 10i. So if I took the conjugate, which is 2 minus 10i, 2 minus 10i divided by 2 minus 10i, that of course equals 1. So if I multiply this fraction here times this fraction here, aka 1, what you'll find is that the denominator will end up being a real number, and that's, then you just carry out that basic mathematics there, which I can't do with a cursor easily. So that's essentially, the rundown on the basics of complex numbers in a nutshell. So what I'd like to do now is see if y'all are awake, and I'm going to give you some questions here. Assuming you're still there. I can't quite see who's around, who's not. So anybody want to answer this question here? What is I cubed? Is it 1, I, minus 1, or minus I? Anybody? You got a few answers here. Okay, that means there's some people out there. That's cool. Oh, interesting. All right, so this is good because not everyone's getting the right answer. Awesome. That's why we're here. If you all got the right answer, I'd be worried. And I got a chat thing going here. Hold on. I thought I turned the mute off. Oh, rats, I had it the wrong way. Crap. I mean, golly. Forgive me. Yeah, so if you want to speak, you can speak. Here's the poll. I'll share the results. So there are a few wrong answers in there. So good, you're in the right place. That's what we want to work on. So I'll just go back really quickly. Those of you who got the right answer, pat yourself on the back. But those of you who don't, that's okay. Ultimately, though, I would say when we are in the business of programming a quantum computer, we're going to have to get a question like this ingrained in our brain, so so that it becomes second nature. It's not hard. It just comes from practice. Obviously, it's not. This is clearly not hard. But it's I cubed is minus I. So kudos to 8 of you and the others, 4 of you. So 1/3 of the group got the answer wrong. So you're in the right place. That's cool. Very cool. So yeah, so take note of this because we're going to be using I a lot in the gate model. And what's even more interesting is we're going to be using it in matrices. So it really does, we really do want to get this down to be second nature over time. So let me stop sharing that. And I have another poll here. You guys didn't know I was going to give you some questions. Okay, so I just launched another question, and that, I hope it's readable, is 3 minus 2i star. Three minus 2i star. All right, so the first curveball I'm tossing you as, what's a star? So recall the star is the conjugate. Remember the conjugate, we had two ways of signifying the conjugate, and that is with a star, or in some books they'll use the bar. They'll use the star, I think, just to keep it, make it nice and easy to type in. So let me end the poll and I'll share the results. So we got we got 9 got it right, which is good, and 1 got it wrong, which is fine. So whoever got it wrong, I probably think that you will never forget that the star is conjugate. Okay. Oh, and by the way, yeah, so the answer for conjugate, now that we know that it's a conjugate, is you just reverse the value of the imaginary part, which in this case is -2. So it's 3 plus 2i. Oh, did I not share the results? Sorry. Yeah, the polling has a, I see the poll, then I have to launch the poll, then I have to stop the poll, and then I have to hit another button to share the results. Then I have to hit another button to stop sharing it. Man, I'm getting buttoned out. All right, here's another question. Are you ready? Anybody? I think you can see that. So that's a vertical bar. I don't think I can increase the size of the font. Vertical bar, 4 plus 3i vertical bar equals. We've got 2 answers so far, so take your time. Pull out a pencil or pen. Do it. We're going to need this stuff to be second nature when we're working with the gate model. Now there are 18 of you out there, 17 of you out there. I'm only seeing 9 answers so far. You guys are just like university students. Let me give it 15 more seconds. You guys didn't know I was going to be quizzing you tonight, did you? Surprise quiz. Okay. So we'll end. Let me share the results. And it's freaky when the majority's right all the time. The real world doesn't work like that. Yeah, the answer is 25. Why? Well, as I wave my hands around, I'd love to write it out for you, and I apologize again for my pen that does it. I got to figure it out. Think about, first of all, the vertical bars means what it's a modulus or the absolute value, right? And then, so what that means is it's the distance from that point to the origin. And if you could see my hands, I've got a triangle here. And so you could think of it as a right angle with one side is 4 units, and the other side is 3 units, and then you take the 4 squared plus 3 squared, which is 16 plus 9, you get 25, and you take the square root of that. So again, the main point here is that absolute value is just one of those, the Pythagorean theorem thing where you take x squared plus y squared and take the square root of that, and you get the distance there. So Good. I'm glad we're getting some incorrect answers. That means I'm not totally boring you.
Hey, Terrill,
Yeah.
your question was modulus of 4 minus 3i, right?
4 plus. Okay. Well, it said 4 plus 3i.
I'm sorry, 4 plus 3i. So shouldn't it be
But if I may, it won't matter if it's 4 plus 3i or 4 minus 3i.
Right. And forgive me if I missed something. Shouldn't it be 5? The answer shouldn't be 5 or something, because 4 square plus 3 square and square root of that, right? So it's just modulus of 4 plus, not 25 or something, right? Forgive me if I'm wrong.
You ain't wrong, man. I planned that.
Okay.
No, I did not. I did not. Oh, man. Way to speak up. Excellent. The majority is wrong. I'm going to put that in a real quiz someday. That's right. The answer is 5. It's the square root of 5. The square root of 25. Thanks for speaking up. Awesome.
Yeah, no problem. Yeah.
Shame on you, 6. Or 5 others at least. Good. At least I know you guys are paying attention. Oh, 25. I'm an idiot. All right. So, oh, wait a minute. I didn't share the results. Yeah, there we go. So, yeah, I planned that. Oh, God. Okay, I think I have another one here. Yes. And I'm going to check my answer before. Oh, God. Hold on. Take a breather for a second here, people. Okay, let me one more problem. I just launched it. Go ahead. I guess you guys can figure out what I just fixed. Oh no! I'll tell you what that means in a minute. Come on, I've only got 4 answers. This one everybody should be able to get in a heartbeat. Just about everybody. All right, good. I'm glad I'm doing this poll. 5 more seconds. Okay, and polling, and I'm going to share the results. So, good. We got a couple more that want to just get straight. So, this sharing the results. So this is -4 right here, -3 right here. So the point is right here. So what we want is the distance from this point to the origin, and it's just a regular triangle, a right triangle with 90 degrees. And so again, you know, the curveball here is these negative signs. So just think of the complex number is I have a point that's -4, 3. -4 minus 3 is right here. Okay, so the distance from here to here is 5. Now, if I had 4 -4, 3i, it would be here. The distance would be 5. If I had 4, 3, it would be here, the distance would be 5, and if I had 4 -3, the point would be here, and the distance would be -5. So good, we got a couple of you with, I gotcha. You guys got me going from 25 to 5, but you know, this is this is the kind of thing that we need to just train ourselves so we this stuff becomes second nature. So good. Glad we got a couple incorrect answers. I think that's my final poll for tonight, people. All right, so let's get moving here. So I got just running through Python, and if anybody has questions or comments, please do shout them out, especially if I got something wrong again. So again, the letter J, capital or lowercase j, is used in Python instead of I. So here you represent one I or one J in Python, and you could use capital letter or lowercase letter. So here you have 1J times 1J, and which is essentially what? It's J squared, which comes out to -1, right? And 0 times J, or 0 times I, is 0, so you end up with -1. So this is the same as I squared. And in Python, you have this, I guess they're called functions, I guess, where you can give the rectangular coordinates. So you can just say 2, 3, and it's essentially the same as putting it in standard form. Here, if you have an assignment statement, taking a complex expression and assigning it to a variable, then you can identify the real part here by saying real, and imag is the imaginary part. Notice it's returning real numbers, etc. So you could also do the conjugate. So here the conjugate of 2 plus 3i is 2 minus 3i. There are several other built-in functions, absolute value of 3 plus 4j. As we found out, it's not 25, but it's 5. I forgot what POW is off the top of my head, but I'll just skip that for a moment. There's also a lot. Yeah, what was that?
Exponential power.
Oh, yeah, thanks. Yeah, I want to take that out because I didn't want to cover that here. Thanks. So it also has a standard module called CMath, and that's where you can get into some of the trigonometric functions, etc. So that's a review in 45 minutes of last time. So let's talk about trigonometry, and I suspect some of you will catch me on some errors here, so please do if I get something wrong. But trig is essentially the study of relationships of the sides, the length of the sides, and the angles in triangles. As a reminder, just to feel good, triangles have 3 sides, and they also have 3 angles associated with them. The 3 angles always sum up to 180 degrees. So this angle plus this angle plus this angle equals 180 degrees. A right angle, a right triangle, is a triangle whereas one of the angles is 90 degrees. And if you think about it for a minute, if one angle is 90 degrees, then the sum of the other 2 angles totals up to 90 degrees. This stuff is relevant as we go, so you'll see. So one thing in trig to be very comfortable with is if you had an angle, they'll use the symbol theta, the Greek symbol theta. If theta is here, then we refer to this side over here as the opposite. If theta is here, then we refer to this side here, which is opposite of the right angle, as the hypotenuse, and this side here we refer to as the adjacent. So if I had a right triangle here and I'm referring to this angle here, then this side here is the adjacent. This is the hypotenuse because it's opposite the 90-degree angle here, and then this side here is the opposite. So that's the way to be thinking about things. So trigonometry, I remember learning this, I guess it was in 8th grade. is really cool because there's a relationship between the angles and the lengths of the sides of the triangles, no matter what size of triangle you're working with. So here I have a triangle that has an angle that has a side 5. Here's another one with the hypotenuse side being 10, and here the adjacent side is 4. Here the adjacent side is 8. Here the opposite side is 3, and here the opposite side is 6. And so these angles, I'm telling you, are the same because we know that because the relationship here between this triangle and this triangle is essentially times 2. So every side on this triangle times 2 is the same side on this triangle. So 5 times 2 is 10, 3 times 2 is 6, 4 times 2 is 8. Therefore, this is the magic of trigonometry. We know that this angle and this angle are the same, this angle and this angle are the same, and of course this angle at 90 degrees and this angle at 90 degrees are also the same. So I hope this is bringing back some flashbacks for some of you. If it's new material, I'm going to be going by a little fast here, but feel free to reach out to me if you want to get more information on trig. I can point you to some videos that will probably do a far better job than I'm doing right now. But because of this relationship of the sides in triangles and the associated angle, we have some I guess they're functions. One function is called the sine. So I can refer to the division of, the sine of an angle is the length of the opposite side, this one here, divided by the hypotenuse. So here, if I had the sine, let's say this angle is x, the sine of x is the opposite 3 divided by 5. So here the sine of x is 3 divided by 5, which is 0.6. Here I could take the same thing, the sine of this angle, I take the opposite divided by the hypotenuse, and the sine again is 0.6. So whenever I really want to think of, equate, if you will, the angle with the opposite side, essentially, then I would refer to the sine function. Also, the cosine is essentially the same thing, except I'm referring to the adjacent side. Adjacent divided by the hypotenuse, adjacent divided by the hypotenuse, in this case is 80%, and in this case is 80% or 0.8. Now we also have the tangent, and the tangent is where you take the length of the opposite side and divide that by the length of the adjacent side. And so here 3 divided by 4 is essentially 0.75, and 6 divided by 8 is essentially 0.75. So these functions here are ways of taking the lengths and associating them with an angle in that triangle. So it's very helpful to be able to understand trigonometry and these functions. So now if you took the time to do the math, as I would do with a pen right now, I could show you how it works out, but you take the tangent, which is the opposite side, divided by the adjacent side, meaning the length of each of those. It really comes out to also being the same as the sine of that angle divided by the cosine of that angle, which does come into play in some of the books I've seen on quantum computing. So you'll see sine divided by cosine, and sometimes you'll see tangent being used. And an important thing to keep in mind is there's such a thing as arctangent. And arctangent is where you have the function is referring to the degrees here, the angle. Well, here, if I had this here, and this fraction here, I had the two sides, and I wanted to know what the angle is there, then I would refer to that as the arctangent function. So what's the arctangent of 3 divided by 4? That would refer to theta, or the angle here. You want to be careful.
Also, a small typo there. You should have tan to the minus 1 of tan theta equals arctan.
Tan to the minus 1. So this right
So where
here.
you've got theta, you should have tan theta there to make it equal to the next bit of text.
Tangent. Yeah. You're saying
tan
this
minus 1 of
theta.
No. So no, that was correct as you had it there. So tan theta over there, but to the left of that, where you've got tan to the minus 1 of theta, you should change that to tan to the minus 1 of tan theta, because you're doing the inverse operation, and that's why you eventually get back to theta on the very right-hand side.
Yeah, okay. Let me highlight this for myself to fix later. All right, thanks. The main thing is that arctangent is referred to quite a bit. So, so here we've got some more angles, and to give you an example of a 45-degree angle, which is very common in quantum computing, we've got the same phenomena here, where the sine, which is the adjacent divided by the hypotenuse, so the sine is 1 over the square root of 2, and here the sine is 2 over 2 times the square root of 2, which is essentially the same as 1 divided by the square root of 2, etc. So now imagine you had the complex number, and you imagine this was the complex plane here. I have x and y, but it's a complex plane, so oftentimes we'll refer to as the x value as cosine of theta, if this is theta, and we'll refer to the y value, or perhaps the I value, as the sine of theta. And so this is one of the things that just confuses people in reading the books. So the point is that we're referring to the same thing using these trigonometric functions. You'll also see the rectangular coordinate. As I said here, you'll see it in this form here, where you have the rectangular coordinate cosine of theta, comma, sine of theta. So this is something to watch out for. There are some common angles, and this chart here, I go to cosecant and etc. But really pay attention. The key here is this gets used a lot. We've got 45 degrees, which is essentially in superposition. And so you'll see the 1 divided by the square root of 2, but you'll also see that referred to as sine of 45 degrees in many cases. So so that's a pretty rough introduction to trigonometry and the functions, and they are important. So let me move on to polar coordinates. So polar coordinates are where we take the rectangle coordinates, and we start to refer to those points as So here is a coordinate, the rectangular coordinate would be x comma y. Instead, what we'll start to do, that same point, x comma y refers to this here. Instead, in polar coordinates, what we're going to start to do is refer to the same point, there's no difference, as r comma theta. So the length of the hypotenuse, comma, the degree that is here. And if you recall, I guess it was maybe geometry, there are 360 degrees in a circle. And so here, the 45 degree, for example, would be between the 0 and 90 degrees, split in half, and that's superposition. So sometimes you'll see that as 45 degrees. So as a reminder, you've got angles here, 90 degrees. If you go beyond 90, you're basically, you go up to 160. This is 180 here. You typically go in this direction. So 300 degrees in this direction is essentially the same as minus 60 degrees. So if I had a point here, the theta would be 300 degrees, but you could also say this same point would be minus 60 degrees because you go this direction 60 degrees. By the same token, you could go minus 200 degrees, or you could go 160 degrees. So that's something to keep in mind there. The direction, the minus or the positive direction doesn't really matter in our case, but they are the same. They are the same thing. So that's a gotcha. Now moving to another aspect of theta, the angles. You could also refer to the 45 degree angle as pi divided by 4. So if you go back to your school days, remember 2 pi r squared was the circumference of a circle. So this is used a lot. So when we refer to pi, we're also referring to 180 degrees, or could be referring to 180 degrees. So you would see r, the coordinates r comma pi. In this case here, 45 degrees would be pi divided by 4. So you would see the pair r comma pi divided by 4 instead of r comma 45 degrees. And so keep in mind here, if I just simply had the point 2 comma pi divided by 6 over 6, I have this point here, I could negate that by just changing the length of r to be a negative number, and it would essentially flip me over to this point right here. So be careful with r being a negative number, or just changing the sign of r, which does occur in quantum computing. So getting back to it, so x is essentially r times the cosine of theta, and y is equal to r, again that's the radius or the length, times the sine of theta. So you could refer to the point x comma y as this point right here. So going between the Cartesian or the rectangular form to polar, you essentially, we already have done that. We've figured out r, but to figure out the Alexa, stop. So here, if I had the the rectangular, y divided by x, for example, that would be the same as the tangent of theta, and so I would do the the arctangent of y divided by x. And so here's how if I had the sides, I could get the theta. And I have this in here just to, time won't allow to go into it, and I don't have my magic pen, but keep in mind if you had the sine of theta, the sine of theta, an angle, plus 2 pi, it's the same thing. It's a full rotation around. It has the same value as the sine of theta, and so on. So, these are some things, I don't think you need to memorize them, but you want to be aware of these various tricks, because I've seen different forms of the same thing in various books. Quickly getting into the Python aspect, and I need to really spend more time on this, we all do. I just want to get it into your minds for another day. When you work with the polar representation in Python, you also have in the CMath function, in the CMath module, you can also get the polar coordinates, etc., and it will work fine. And we'll talk about phase another day. You could also get the rectangular coordinates as well, that transform it into a complex number. And it has the sine and cosines, etc. So I'm going to end here. I do want to just start to whet appetites, and again, it's kind of weird because this audience, many of you know this quite well, but for newbies, this is really rocket science. Well, next time I'll hold a session like this, I'll go over the trigonometric stuff again in a little more detail, and I'll start to introduce you to Euler's constant E and how it's used in this space. This is another thing that took me quite a while to get over. Euler's formula, Euler's identity, is used a lot and in quantum computing, and we'll cover that more at length next time I have a powwow like this. But yeah, this here, I'm sure, stumbles a lot of new people, myself included, as this was totally out of my domain. I went through business and computer programming in my college degree, so I was never exposed to Euler's identity or anything like that. So next time I'll hold a session like this, I'll also cover the unit circle. We'll be taking those trigonometric functions and applying them to the unit circle. And the cool thing about the unit circle is we get rid of r. R, the radius is 1, so that really simplifies a lot of that trig stuff. We'll get into Euler's formula and how that is used, and notice the complex number-like form here. So we'll talk about that, and then I'll have some pretty cool interactive things with phasors, and talk about phase factors. And here's where, it's almost like an aha moment where you see why we're dealing with this unit circle and how it relates to curves, or waves rather, and we'll cover more about that next time. So that's all I have prepared for tonight. It's Euler. Yes, probably said it incorrectly, but we'll cover that stuff more next time. So any questions or comments, particularly questions from the newbies, those folks who are new to this stuff, feel free. Let me stop sharing here. Get back to being, wow, some of you are still there. Keeper, what are you doing here? This is like second nature for you.
Hey, can you hear me?
Yes, I can.
Good. Well, it's a good review, and really, you know, aside from having an awesome evening, on my couch and understanding what your perspectives are, it's just good to, be a part of the community and see other people, here. But from my perspective, complex numbers, and it's not really an intuitive thing, and you have to understand the rotations and, get your mind out of a straight line and start thinking circularly. One thing I like to do is go to Wolfram Alpha and, you can type in Euler's equation and you can plot it in X and Y, and you can actually see, how cosine and sine interweave and kind of makes like a bubble surface,
Yeah.
so that's really cool. It's my favorite topic really at the end of the day, to describe how particles actually behave in the complex. So
Sweet. We now have a topic for your talk.
wonderful.
Excellent.
Excellent. Thank you.
Yeah, I didn't mean to cut you off there, but yeah, just strategically, I mean, it's this level of information I think a lot of us need, myself included. I just never learned this stuff, or actually I was exposed to it, but I didn't care. Now I care. And I think a lot of people are like that. So, definitely a better instructor is better. But, it's this level of education that we need to, work with. So.
Well, one thing, it's just, relating it to the physical. So, remembering that we're talking about magnetism. Sorry if you can hear my kid in the background. He's watching a show. But, relating it to the physical and understanding, well, okay, when we look at a qubit, what is this particle? What kind of, is it an electron or a photon or or even a proton? And how does the magnetism, relate to the complex? And, in chemistry, what happens is we take the z direction to be our magnetism, right? And so you can be up or down along the z-axis, and this is your 0 and 1 state. And then how does that particle, rotate in the complex plane? And then you have your superposition states of you can be both spin up and spin down at the same time. And that's really where the magic, comes into play. So. Yeah,
but if you don't get the basics down, and I think that's where a lot of us, are caught up. That's what we're trying to do here. Then when you start talking about the complex space, we know what that is, right? I'm talking about, the new people like myself. So, that's what this series is about. So, yeah, anybody else have anything else to toss in here? Thank you, Keeper. But yeah, we got to get you to give a talk just on whatever you just talked about. If we get the basic math into this cohort of this community, and then so that we're tuned up on the math, then you can take us to the next level.
Wonderful. I would really appreciate that.
Well, not as much as we would.
Well, thank you. Thank you very much for hosting these. Sure. I really enjoy it, whether or not I can actually participate in the quiz or not. So.
Oh, were you one of those with the other answers? Or did I bust you on the 25?
No, actually I wasn't able to respond to either one of them. I'm sorry.
All right, well, I'm taking names next time.
Okay.
Let me see. Yeah, any other last calls? Yeah, Ram, yeah, there are boatloads of video links in this stuff, and frankly, the challenge is to sort out the great from the average, from the terrible. So actually, I'm trying to figure out a way to do that for the community, because I think it's a necessary. There's just so much out there, but there's some really good ones. and, you know, figure out a mechanism so that it's not like Terrill decides which one's a good one and bad one. Somehow we get the community to work that out where the best ones bubble up. Yeah, Khan Academy are definitely great ones. You know, I think it's 1 blue, 3 brown, or 1 brown, 3 blue blows even Khan Academy away in being able to you know, give you visual pictures. But if I were to think about it out loud, I'd start with Khan Academy, go to 1, 3, 1 blue, or whatever the number, whatever it is. And then there's another recent channel that's come up that just takes the visualization to another level from 1 brown, 3 blue, or whatever. And if I get a minute, I'll put it in the show notes for tonight down in the you know, the message for this evening, so you can get those links. No, I know what I'll do. I'll put it in the archives for tonight. So, you know, where you can get the link and all that kind of stuff for the recording, I'll put it in that same spot. You guys, you know, I hope you know what I'm talking about. It's this, give me a second here. Yeah, it's this location here. So I'll put some stuff in here for the community. Into this site here. This is where you put the record. I put the recordings and any artifacts. Yeah, 3 blue, 1 brown. Yeah, it's great job. But there's even a better one after that. So anyway, last call for any questions or comments. Get you guys out of here. I don't know about you, but this is like, we're in 2.5 weeks of this Quantum-A-Palooza binge, man. I am fried. And some of you have got to be too. Jamie and Amir, Keeper, and everybody, George. And last thing, did anyone watch the Led Zeppelin Quantum Break I offered to everybody? Did you see that link there? All right, well, I enjoyed it. All right, I'm rambling here. Good night, folks. We'll see you next time. Tomorrow, definitely check out Matt, and all the videos are up. If you had not had a chance to follow Matt on his first 3 episodes, they are available. They're running a little shy of 2 hours, so you got a lot of binging to do before tomorrow if you haven't seen them. But we'll see you tomorrow night for episode 4. So thanks, folks. Appreciate it.
Thanks. Bye.
Thanks.
See you, David. See you, Cynthia.